Hello, viewers. In today's session, we are going to discuss another important and conceptual problem from integrals. And in this session, we are going to discuss this definite integral in which the integrand is greatest integer function. So here we have to evaluate this integral where the limits are from e square to e raised to 4, and the integrand is the natural log of x minus 2, right? So here we'll see how easily we can solve this problem by making use of the concept of integration by substitution method and the definition of greatest integer function, right? So let us start. So let us call this integral as I, right? And here the integrand is the greatest integer of natural log of x minus 2. So let us make the substitution that is t is equal to a natural log of x minus 2, right? So we can now write t plus 2 is equal to a natural log of x, and by definition of logarithms, we can write x is equal to e raised to t plus 2, right? So the relation between x and t can be written in this form. So now differentiating both sides with respect to t, we can get dx over dt is equal to d by dt of e raised to t plus 2. The derivative of the exponential function is the exponential function itself, and then by chain rule we have to find the derivative of t plus 2, right? So we can now write dx over dt is equal to e raised to t plus 2, and here the derivative of t is 1 and the derivative of 2 is 0. So here we are left with only 1. So we have e raised to t plus 2. So now we can write dx is equal to e raised to t plus 2 and dt, right? Okay, now let us change the limits, and here x varies from e square to e raised to 4. So when x is equal to e square, then the value of t can be obtained from this relation. So we can now write t is equal to natural log of e square minus 2. Substituting x is equal to e square in this relation, we can now write 2 log e minus 2. So this is 2 times 1 minus 2, because natural log of e is equal to 1. So this is 2 minus 2, that is 0. So when x is equal to e square, then the value of t is equal to 0. Now when x is equal to e raised to 4, then the value of t can again be obtained by using this relation. So we can now write natural log of e raised to 4 minus 2, and by using the properties of log, that is log m raised to n is n log m. So we have 4 times natural log of e minus 2. So this is 4 times 1 minus 2. So t is equal to 4 minus 2, that is 2, right? So when x is e raised to 4, then the value of t is equal to 2. So we conclude that when x varies from e square to e raised to 4, t varies from 0 to 2. So now we can rewrite this integral I in terms of t. So we can now write 0 to 2. Here t is equal to 0, here t is equal to 2, and we have greatest integer of t, because natural log of x minus 2 is t, and for dx we can now write this expression. So we have e raised to t plus 2, and here we have dt. So now we have to evaluate this integral, and we see that the limits of integration varies from 0 to 2. right? So let us represent these two numbers, that is the lower limit and upper limit, on the real number line. So here we have, say, a 0, and here we have 1, and here we have 2, right? And we can see that the limits of integration are from 0 to 2, and between 0 and 2 we have this integer 1, right? So whenever we come across with greatest integer function, we always search for integers, right? So we'll break this integral as a sum of two integrals. So the first one is from 0 to 1, and the second one is from 1 to 2. So we can now write I is equal to I1 plus I2, where I1 goes from 0 to 1. So we have t is equal to 0, here we have t is equal to 1, and the integrand is greatest integer of t. Here we have e raised to t plus 2 dt, and I2 is from 1 to 2. So we have t is equal to 1, t is equal to 2, and the integrand is greatest integer of t, and e raised to t plus 2 dt. So now we have to calculate these two integrals, right? And here we'll make use of the definition of greatest integer function. Now see, here t varies from 0 to 1. So t lies between 0 and 1. So when t lies between 0 and 1, then the value of greatest integer of t is 0. And when t lies between 1 and 2, that is the t is greater than or equal to 1 and less than 2, then the greatest integer of t must be equal to 1, right? So now we can rewrite these integrals as 0 to 1, and here we have 0, greatest integer of t. So this is 0. Here we have e raised to t plus 2 dt, and then we have 1 to 2, and here we have greatest integer of t is equal to 1, and here we have e raised to t plus 2 dt. So now this integral here it vanishes, the value of this integral is 0, and here we have 1 to 2, and e raised to t plus 2 can be written as e raised to t and e square, and here we have dt. Taking e square outside the integral, we have 1 to 2 e raised to t and dt. So now we have e square. The integral of e raised to t is e raised to t, and here we have limits of integration from 1 to 2. Now substituting the limits and taking the difference, we have e square. Here we have t is equal to 2, then we have t is equal to 1. So here we have t is equal to 1, so this is e raised to 1, right? So the value of this integral I is equal to e square times e square minus e, which can also be written as by taking e common here. So when we take e common, it gets multiplied with e square. So this is e cube, and here we have e minus 1, right? So the value of this integral is e cube times e minus 1, or we can also write this expression as e raised to 4 minus e cube.